is awesome. Okay, so what we're going to do is up to a little high point so that we can have a really nice 360-degree vantage of this whole area. While we're up there, I'm going to kind of go through some of the regional things we're seeing, introduce some concepts in lab, lecture, dinosaur class. I know you guys, we talked about this at the beginning of the class, but we'll bring it back in and tie it up. And then we're just going to kind of follow the rocks as they get younger. So we're going to start kind of west, go towards the east, and we'll go younger rocks, different environments. And so, yeah, we're just going to kind of take our time and mosey through. If you see something really cool, please shout out and ask. So this is supposed to be just a really like laid back field trip. We're just out here having a good time, doing some geology stuff, soaking in some nature, right? I'm going to keep it at a very introductory level. It's really easy for me to get lost in the sauce and go very in depth, but I'm going to keep it very simple, right? But if you have more in-depth type questions and you want to know about it, it's the time to ask. All right, let's go for it, guys. This first bit's the most strenuous. After that, pretty flat. Just getting up to the little high point, and then everything else is kind of down. So, what we're standing on right now, the brown stuff is very, very recent eroded material. The white stuff, though, is really, really old gypsum. So as we walk by, feel free to pick some up. It's a little sharp, be careful. There's probably some modern day gypsum around, so I'm looking for it. It'll look very glassy and glinty in the sun. So look for stuff that's glinty. That's probably modern day gypsum. But feel free to pick up the stuff as we go and take a look at it. Okay? Can we collect here? Yes, it's not the bones, but you can collect the rocks. This way. There's a cliff. Come on. Everyone, soak it in. Come on up here. Not too close to the edge. I will be a barrier.
You can see those layers.
Yeah, so take turns coming up here so you can really look down into the bowl. Head.
What is
The benchmark. So remember when we talked about benchmarks in lab? So you can look and see what the exact elevation is of the point from the USGS survey. Go for it. So those of you who are in my UNM Valencia lab, last week we talked about benchmarks for topographic maps, geologic maps, fun things like that. There's one right here if you want to come take a look at one in real life instead of the photo I showed you on the screen. And so a benchmark is a very precisely exact known location of an elevation. So you can look and see right on this rock, they've stamped the exact elevation of this spot, coordinates or everything are well known. So we create our topographic maps and ultimately our geologic maps based on these very precise measurements. Yeah, definitely worth a look. It's really cool. Okay, so first thing I want to do before we look at our sheets, but I just want them out. What do we see in the distance?
Sandias.
The Sandias. To the north?
Nacimiento.
The Nacimiento Mountain? kind of to the northeast, what do we have?
Hamus.
Jemez Mountains. And then a few people pointed it out, but there was like that little upright feature that direction. That's Katmazon Peak. It is an ancient cinder cone, and essentially it's eroded off. So when we look at cinder cones, right, they have that really cool cone shape to them. That is all very loose material. Through time and erosion, that stuff goes away, and what's left is the neck of the volcano, where the magma would be coming out onto it, right? That solidifies and crystallizes, so it stays, but everything else goes away, and we have what's called a volcanic neck, or sometimes you'll hear them referred to as a plug. Now, Katmazon is very young in terms of geologic time. It's only a few million years old. Everything else that we're seeing here is hundreds of millions of years old. Then there are rocks in the Nacimiento Mountains that are a few billions of years old. Okay. So we have a wide range of stuff. The Jemez, most of the Jemez is less than 10 million years old, so still a little bit younger in terms of geologic time. Okay. Our Sandia Mountains, the granite that makes those up, is about 1.4 billion years old. So we're in a unique area where we can see all of these different geologic features because of erosion and weathering, tectonics. And we're at a unique spot in New Mexico specifically, the intersection of three geographic things. Where we are here, the Colorado Plateau is just a bit northwest of us. We have the Rio Grande Rift, which many of you drove up. So we're in a very unique location where this geology is. And so it's a really special area to see where we have the intersection of all these places together at different ages. When we zoom in to where we are, in general, the same time frame that the Rocky Mountains were being built from a mountain building event, we call that an orogeny. So stuff is colliding. What type of plate boundary would that be by geology? Convergent. Okay. This convergence, though, is happening way off the coast of California. So how the heck do we get mountains that form so far inland? When you think of mountains forming from convergent plate boundaries, what are some places you might immediately think of?
The Andes, Himalayas.
The Andes, Himalayas, Pacific Northwest. Those mountains are really close to the coast, right? But this particular collision event that happened off the coast of California uplifted the Rocky Mountains. There's something really unique that happened during this mountain building event. When we have convergent boundaries, what happens to our plates? We've got two plates coming together. One subducts, right? One gets pushed under. That usually happens at a nice kind of 45-ish degree angle. Not always, but usually. What happened this time is that plate started at the nice angle and then flattened out and caused buckling further in on the continent than normal. That's what uplifted the Rocky Mountains. The extent of that buckling is the extent of the Rocky Mountains, and that includes our Sangre de Cristos here in New Mexico, and it includes what we're standing on. So we have a signature of that collisional event right here where we're standing. Now, it didn't form the different ones we're looking at. Those are about 200 to 90 million years old. This collisional event happened about 60 million years ago, and I'm approximating the result of the Rocky Mountain uplift. Everyone with me so far? Do these rocks that we see, do they look Horizontal, remember we've talked about the principle of original horizontality. Do these look horizontal to you? Or do they look kind of like tilted? They're tilted. Which kind of way are they tilting? Are they tilting this way or this way? Right? They're tilted up like this. Yeah. Now, we're going to walk over there, and I'm going to ask you the same exact question for the rocks on that side of this bowl that we're standing on. So let's go over there. Okay. So, where the white and red rocks are, do they look like they're tilted?
Kind of, but not much.
I know, it's a little hard to see from here. They are tilted. The ones in the background, not so much. They're tilted this way.
Yeah.
So we have rocks that are tilted this way. Can we think of any geologic where our rocks are tilted that they would then meet? Anticline. What is an anticline? It's folded rocks, right? And so we've got our rocks that are tilted, and at one point, they were connected. This whole area would have been a hill, a big hill, and we would not see into it. Okay, so it would have looked like this, right?
And then
What happened?
it snapped.
Step. It eroded away. Okay? And this anticline, this folded series of rocks, is from that same collisional event that uplifted the Rocky Mountains. So when we see folding in rocks, it's compression that's doing it, right? If you were to take Play-Doh and put layers of Play-Doh on top of each other and then squish it together, what would happen? You would kind of squish up, right? On a very large scale. Okay, so the colorful image you see there on the paper that I'm giving you, we call this a stratigraphic column. Okay? What it is a representation of the different rock units in an area that lay on top of one another. Okay? And it goes from oldest at the bottom to youngest at the top. Okay? Now, sedimentary rocks are weird. We like to lump them into what we call formations and members. So when you look on that little map, the little column there, you'll see something on the right-hand side. You'll see the Chinle group. Right above it, you'll see the Todilto formation. And then in tiny little font to the right of that, there's like names and then MBR. That means member. So formations are essentially a group of sedimentary rocks that share similar characteristics and qualities, and then within formations, we can get even more specific, essentially. And we can have little members that might be slightly different from the overall package of rocks. So we kind of subdivide them in that way. Okay? So there are names for each of these things. Okay, so you can see there's the Todilto formation, there's the Summerville formation, there's the Morrison formation. Then there are 3 members in there, and we are going to talk about them in detail when we kind of walk over it to that area where the yellow rocks are. Kind of over there. Okay? There's a lot of red near the bottom, right? There's a lot of red stuff. That is the Chinle group. That is that very low one there. That formed in the Late Triassic period, say about 250 to 205 million years ago. Now, on your document, I've given you a little description of what's in the Chinle group. So it's a series of red-colored mudstones or shale, siltstones, and there are some features that we find in them. There's really small ripple marks, and there's mud cracks, but there's no fossils, certainly no marine fossils. Okay. So I ask you in this question, and I give you the answer, but we want to think about rocks and the features we find in it, and whether or not we find any fossils and what that means. And we call this the depositional environment. So in this case, we have siltstones, we have some mudstones, we have a little shale, we have some small ripple marks, mud cracks. Those are indicative features of floodplain, right? Where it's periodically wet, keep pretty low energy in terms of not a lot of fast water, so you can get very fine-grained rocks. We can get some small ripples, there's water moving over it, right? If you go down to the Rio Grande or any stream where you can see rivers dipping in the sediment. And there's no fossils, specifically no marine fossils. So that right there nixes out an ocean environment, which is so nice. So in this area, 210 to 205 million years ago, this was a floodplain. Right? It didn't have the sand dunes. We didn't have all the mountains. We didn't even have the Rocky Mountains. This whole kind of western U.S. area was a series of floodplains with rivers coming from highlands that were kind of like East Texas. So kind of really trippy to think about, right? We didn't have the topography and the geography that we have right now. So this area would have looked very different. It would have been flat. It would have been just sort of an open plain where you had large river systems moving through, depositing material in water. Okay. Totally different environment. So that's the Chinle. That's the red that you see. The red off to the distance, that's very bright red, sort of a deeper red, is an entirely different unit. Totally different rocks. So when we walk around, we'll see more of the red as we look into the bowl. It is the bottom layer from the Late Triassic called the Chinle group.
So then with the layers, like, does the top layer, like, stretch all the way back to, like, there because things kind of, like, shifted up and, like, layers are super deep?
Yep, one of the top layers is off the distance, and I'll point it out when we get over there.
Okay, because I was like, a lot of this is seeming to be mostly that red stuff and then, like, a couple layers.
Yep. So right now, we are not standing on the Chinle. This is not red. This is gypsum. So we're moving up in time already. So if you look at your stratigraphic column, we are now at something called the Todilto formation. Okay? And you'll notice something interesting. Does it say anything about the early Jurassic on this column, or does it jump right to the middle Jurassic? It jumps to the middle.
Somebody didn't proofread.
So we talked about relative age dating in both my labs. There's a time jump here. That squiggle that you see, the black squiggle, represents that time jump. So that indicates erosion happened, right? We talk about unconformities being an erosive time frame. So we're missing the early Jurassic. No, we don't. We don't have it here. I don't know if it's exposed like further north. I don't remember. But we don't have it here. So we're missing that entire time. We don't know what happens. So we have to jump into time a little bit further. And we jump to about 159 years old. Now, the Todilto formation, where we are here, we don't see all of the members that are indicated there next to it. You can see there's the Tonke Arroyo member, the Mesa Lucero member. We don't have those here. And that is normal. That is totally normal. Okay, if you think about, let's just think about the northeast coastline. Go from the northeast all the way down to Florida. there's different stuff along that coastline, right? So if you imagine several million years from now, all of that turns into rock, it'll be slightly different as you go down that coastline. So some of it may exist further down, some of it may exist kind of closer. That is totally normal. That happens in our sedimentary rocks. And so that's what we have going on here. So we're missing a few of those members here. That's okay. The main member we have here is the gypsum. The white plateau you see off in the distance is a gypsum line. We use that for things like sheetrock. Or gypsum board, whatever you call it. Okay? That is actually mine still today. You can see if we look across down into these layers, thick, crumbly, kind of off-white looking stuff, that is all of this really thick gypsum. We have a thick gypsum unit. Gypsum's an evaporite mineral. So it forms, right, when you have water coming in and then going out, all that stuff evaporates and crystallizes into gypsum. So think white sands is gypsum, but it's not a rock yet, like we're standing on. Maybe one day it will be, and it'll be very similar looking to this. Right now, it's one sand that you can sled on, and it's like low-key kind of people, but at the same time awesome. If you have done it, if you haven't, 10 out of 10 recommend.
It's too slow.
Too slow, yeah. Okay. So, if we have a ton of gypsum forming, that means we have water that's kind of coming in, and then like, I'm out, going out, coming in, going out, depositing gypsum as it goes. So that means we had some sort of water body that came in and out for a while. And that's noted. I wrote that for you on your sheet. Okay. Now, to see the rest, we're going to keep walking because they'll be exposed better. But we're going to move up through time, and we're going to go take a look at the Summerville Formation. Okay? So that's sort of, again, more middle Jurassic. The crumbliness that you're seeing here is the gypsum eroding. Gypsum is a very weak mineral. It breaks down very easily. It gets very crumbly, which is what you're seeing. Again. Whoa, my God.
Thank you so much.
As we look across first, directly across, what do you guys notice? There's a red to white. What else do you notice? Are some of those rocks like really tilted like everything else?
A little.
A little, but not really, right? Like not like that. Right? Those are really tilted. Those are pretty horizontal. So these are very young rocks here. It's what we call quaternary rocks. Now it's not on your stratigraphic column that I showed you. These formed in the last 2 million years, and some of the stuff on top, the sediment on top that's not yet a rock, is recent. So there's a whole subset of geology called superficial geology or quaternary geology, where you study very modern day rocks. What is modern in geology? Like the last 20 million? Last 2 million is usually what quaternary geology studies.
Yeah, that top layer isn't on the sheet. She printed 2 million and 1 years ago.
There you go, Luke. All right, now what I want you to do is look in this general direction. You can see several different things. Obviously, we see a ton of yellow and purple. We also see to the left a red and a white, stuff like that. There's like a white, red, and some of it's here, this white, red stuff. It's it just looks like, it doesn't look like a rock paper. That is our Summerville Formation. It is a mudstone. When they weather, they are what we call slope formers. So they decorate create hills like this. You could quite literally go over there and slide down it and be totally fine. It's very soft and squishy. We're standing on it right here, right? It's very soft and squishy. Okay, so that is our next unit that we're looking at, right? So if we look at our sheet, what does it say about the Summerville? So the Summerville has tons of mudstones, shale, there's some mud cracks, there's some minor sandstones here and there, okay? So it's a continuation of sort of our floodplain area, right? So we're getting a ton of this looser sediment being deposited. The yellow that we start to see, that is the start of the Morrison Formation. And for those of you who are dino people, that's where all the dinos are. Okay. The Morrison Formation, if you look at your stratigraphic column, has 3 main members. The salt wash, brushy basin, jack pile. Okay. The salt wash, all of the yellow. We're going to walk over in that general direction and we'll see some pieces of it. The yellow over there is the salt wash member. Now it's mostly a sandstone. There's some kind of yellowish red mudstone that's mixed into it. Okay, but the salt wash is very distinctive, being a yellow sandstone like this. As we move up the hillside, we have more of that really soft, squishy stuff right where the trail is, further up there. That's another mudstone unit. More mudstones, shales, that kind of stuff. And then the rocks that are kind of at the top, and we'll kind of walk past them here, is the brushy basin unit. That's where we're going to see our dinosaur fossil. Okay. That's another sandstone. And as we get closer to them, I'll show you some of the cool features that are observed. Things like crossmeds and other structures that tell us about the environment. Okay? Any questions? Excited? Yeah, let's do it. Okay. You can walk down here and touch the yellow sandstone right there, and that is the salt wash member of the Morrison Formation. Here, nice and yellow. Now, this is not anything that I've talked about in any of the classes. All of the cracks. Those are not little faults. Those are what we call joints. Okay? So it's breaking planes of weakness in a rock, but there's no movement, right? So there's no displacement of anything. Okay, so it's just natural breaking that happens in the rock. And you said it comes after? It comes after it's formed, yep. All the little dots, the holes, the pits, we'll see more of this as we walk along. This is a very special type of weathering called Tafoni. Tafoni is really cool. You get essentially little salt crystals that grow into little pore spaces in the rocks, little micro fractures, things like that. And it expands as they crystallize, so it pushes open the rock. And eventually these little pits form. Okay? This is very common here in the desert. It's also very common on coastal environments, but from seawater. So if you Google Tafoni, you'll see some really extreme examples of it. This is very minor, okay? There's a whole, I always forget the name of it, but it's a fear of like the honeycomb beehive texture.
Trypophobia.
Yeah, that. So Tafoni will do that to people. I had a friend in my undergrad who could not deal with looking at Tafoni.
Is the blue stuff the crystals, or is that
That is
lichen?
lichen. Yeah. A lot of biological material. Good stuff though. All right.
Look, I haven't seen blue
Let's
lichen before.
continue on our way. So as we look in this direction, east, that's still part of the Morrison Formation. Beyond that, though, called the Dakota Formation. We will encounter the Dakota Formation. Instead of following the trail up that way, we're going to go alongside the area to see our dinosaur. And we started out, we had some sort of weird evaporite, and if you look behind us, you can actually see how thick some of that gypsum is in this area. Yeah, that's where we were standing, where we started. Okay. And so the Morrison is a series of mudstone, sandstone, it's a big river. That's called the gates of hell. To get down there, you see this slope and then this one where there's like a nice little gully wash. And we make the field camp students go down that. So we're down in here and then we go to our health gate and then we're in the bowl. So we're looking for the dinosaur fossil. The dinosaur in particular is called Todilto. It's in the long neck variety. Yeah, a big bronto looking thing, exactly. Okay. And there's like a femur piece. It's not super big. Take it slow on your footing through here. There's a small piece here, fossil, on this face of the boulder. That brown stuff. There's a little piece here.
That's it.
Oh, the little piece. There's a bigger piece.
Sparse.
I wasn't the one who identified it, but here it is. They look at the structure of the bones that they can see that are preserved in similar units and things like that. So that big brown slab, can you guys see down here? I'll point it out. There is a small piece, but the big one down here that actually looks more like a femur bone. If you look kind of where my hand is, you can see that it has like a very distinct kind of what you would think of as a bone looking like on the inside. It has that spongy thing. And if we were all geologists and this bone wasn't protected, we could put our tongues on it and it would like stick our tongues to it. So bones, because they're porous, they have like a spongy texture, they will lock onto your tongue. That's scary. So geologists, as you guys know, because I probably have said it in every class, maybe not the dino class, but we'd love to put stuff in our mouth that we probably shouldn't. To like tell things about it, but like, here we are.
Said, I think this is uranium.
Yeah, it's probably happened many times. We're a special breed of weird. It's fine, we embrace it. Okay, I'm gonna get off my little golem perch, and whoever wants to come up here can. You can come up this way. This might be a little bit easier than the way I decided to come up here. So I'm gonna come down this way.
These guys are regularly more than 100 feet long, so it could be stretching all across here.
Yeah, these are big dinos.
You ever been to the Natural History Museum and saw the big long neck dinosaur? That's Diplodocus, however you pronounce it.
I say it differently every day. But then again, I say all the geology words different on a daily basis. It's great.
Yeah, you can really tell where the joint is.
Yeah. Isn't that crazy? It's awesome, right?
So this is which formation?
This is all part of the Morrison, and this is the brushy basin member. So it's one of the main sandstone units. Okay. Anyone else want to go up there? You guys want to go up there? Okay, let's make some room so that people can get up in there. Fine. Yeah, did you take a picture of it?
Sweet.
Sorry than I do.
It looks like almost marine.
Yeah. What's like different
Colors and textures from the rest of stuff around it?
Yes.
Is it something interesting or one attack?
Actually, it kind of looks like a cross section of maybe like a rib or something.
Yeah, that's what I was thinking. Yeah, it looks like it's.
Yeah, because you got two definite, maybe third there,
Yeah.
but
Oh, okay.
There's definitely mostly just dinosaur stuff in here. You guys seen photos of the blueberries on Mars? There's little nodules like this on this figure right here. So this face here, you can see them. These little buggers. You can also see them on the boulder here that Jasmine's looking at, right? Okay. These are little clumps of sediment. There's the thought that there's something at the core of these little things that is kind of crystallizing them all together. So they're kind of like baby concretions, but they formed with the sandstone. So you get these little balls of sediment that are preserved, and you can pop some of them off and like keep them. And some of them already are popped off and they're just on the ground, right? So like here's one. Okay. You can see in some parts it's a very white rock. Come on up close and personal to it. It won't bite you. And take a look and see if you can tell me what kind of stuff is in this rock. Quartz. It's all quartz. This is quartz sandstone. Okay, so it's all quartz sandstone, so it's very crumbly. Right? Just pick up some of it and it just kind of crumbles. It's all quartz. Where do we get quartz sandstone forming predominantly? Beaches. Interesting. And what about like coal? Where's coal formed?
Swamp.
Swamps. Huh. So we had a time jump, and now we're in a beachy, swampy area. So we're moving from what we call terrestrial on land to marine. Okay? So this is the start of the Cretaceous interior seaway. So it's this large continental sea that stretches from the Gulf of Mexico north through Canada, and then doesn't really go that much further west of like part of Utah, and doesn't go much further east of kind of like middle of Ohio. So the rocks we see here and the rocks we'll see further are all part of the Cretaceous interior seaway, and they run that whole span. So we can see these same rocks pretty much north south here. We can find them in multiple states. We can find the fossils in multiple states. They look slightly different in certain areas, but it's all the same stuff. Okay, so now, so that environmental change, we're moving from floodplain, okay, right? We have beach, swamp, so we're not quite out in the ocean, but we're pretty near it. Okay. As we move that way, you can see that sort of brownish tan color. Rock right there that slopes off. That is more of actually in the ocean water itself. Okay, that's part of the Mancos Shale. There are some subtleties in there that we won't go for here, but okay. So we're going from a terrestrial environment to a marine environment. We haven't really walked that far, right? So it's pretty cool that we can walk in a pretty short area and see this massive environmental change in New Mexico in like, really what is a square mile if you draw a straight line? Just a whole mile. Looking at 120 million years of geologic time, which is insane. Okay, so we're gonna kind of walk around that way, and we're gonna go back a little bit, and we're gonna sit on what I wasn't able to show you when we were over there because you can't see it very well. We're gonna sit on the other piece of the regional feature that goes with the anticline. Because right now we're still in the anticline, right? So these rocks are still really bit like tilted, right? So these would have all come up and over. Okay. All right. This sandstone here, not the same as this sandstone. That I'm confident about. We're standing on the unconformity. Cool. So we're standing in a missing time, an erosional surface, and it's been filled in obviously through weathering and stuff. But how much time is missing? Like, hold on. I wrote it down on here purposely because I always forget the exact number. Because that's my brain for you. So we do a Cretaceous jump, it's about 125, so about 25 million years or so. Okay, yeah. Alright, when I talked about the large-scale regional features of this area, I left a piece experience these across the valley? No. So we have an anticline that turned into the syncline. So we're standing pretty much on what we call the axis of the syncline. So where the fold is. So that was the other feature that formed, right? If you take some Play-Doh layers and you squish them, you'll have one that maybe goes like this, but one that kind of loops up like a U, right? And I'm trying to do this with my arms, but like they're not broken, so it doesn't work, right? But it would make kind of a curve like this, right? And that's what we have here in the landscape. The rocks did that. So if erosion hadn't happened, it would look like a cool hill like this, hill in a valley, right? It's pretty dope, right? And so now we're standing here, but we can see it. So we saw the anticline, here's the syncline. The youngest rocks are in the middle, the core. So what you're seeing when you look out, all the brown stuff that's on top of everything is the Main Coast Shale. It's a massive unit. Super widespread. The road you drove on, Main Coast Shale. When it's wet, it's pretty much impassable. Why? What's in shale? What is shale made up of?
Clay.
Clay is for days. Thank you, Abby. Clay is for days. So that stuff is worse than ice. Right? So all of this stuff out here is Main Coast Shale. So all of the brown. Well, the Main Coast Shale doesn't just have shale. It sometimes has sandstone in it as well. And so it's another huge package of stuff. So that's kind of what those areas are that are popping out there. The Main Coast is kind of like a long term that we use. So we have different types of rock. So the stuff that's sticking out is stuff that doesn't weather as easily, like sandstone. Remember, the mudstones and shales, those are our slope formers. And so they are kind of what the stuff is being dragged off. In between, all the stuff behind you, the greens and reds, that's all mudstone stuff. So when we have sandstone or other rocks that are not weathered as easily, they'll stand out. Good job, doggo. Okay. Now, it's a little hard to see from here. When we go back out, it'll be easier. I talked about the faulting. There's a big fault that runs through. It kind of dies out down into here. There's traces of it. But the Nacimiento Mountains, so not the little slope thing, but the mountains behind it. That's why those mountains are so straight like that. Okay? That fault is a reverse fault. So it's from the shortening. Yeah. Now, the tricky part is when you read stuff online, there are some other types of faults there that have sort of overprinted it that are from the Rio Grande Rift that happened about 20 million years ago. Right? So when we had our rift, we had stuff being pulled apart. And so as that happens, brittle material is going to snap and break, kind of drop down, push up, do different things. And so the faults behave differently. Instead of going up over, they drop down, they get pulled out. So there are some of those types of faults that are in that area. And so taking apart what's happened up there can be very convoluted. We have some rift faults in here as well, because we're not far from it at all. It's just literally right in there. If we fast forward beyond the Cretaceous to about 20 million years ago, that same slab, that subducted flat, it got stuck on the bottom of the continental lithosphere. And now there's not a for sure answer, but the thought is that it's partially the reason that our rift started. It kind of got stuck, and as it started to pull off, it was pulling on the brittle lithosphere above it, and it started to break it apart. That's a hypothesis when the Rio Grande Rift started. Okay. There's a lot of other stuff happening tectonically around the same time, but that's one of the big things that they think started the Rio Grande area. Okay. And then that plate kind of snapped off, and We honestly don't know what happened to it. Some people think it sunk all the way down in the mantle to the outer core boundary and it's just like hanging out there. Other people think that perhaps as it was kind of breaking off and it's dense, so it wanted to go down, it kind of just remelted and was assimilated. That's a geophysics question, and that's well beyond my pay grade. Okay? But these processes take place over millions of years. So you can imagine that, yeah, there may still have been a plate there. If the Rockies are uplifted, this area is being smushed about 60 to 40 million years. It doesn't happen in one thing. It happens over millions of years. And so eventually that plate's going to do something. And so the times all sort of work out to a nice little puzzle that fits together. Any questions